An object so powerful, so dense, that nothing, not even light, can escape its grasp. Black holes lurk in the depths of space with an insatiable hunger for anything that comes too close. They are invisible giants, silently bending space and time, swallowing stars, and reshaping entire galaxies. Their presence can be felt across the cosmos, including our own Milky Way. Let's journey into the heart of these cosmic monsters, exploring the different types of black holes and their strange properties, with real-life examples that defy belief. From the massive black hole at our galaxy's center to the mysterious phantom black holes drifting in space. By the end, you'll see why black holes are some of the most feared and fascinating objects in the universe. The enigmatic stellar black holes, born from dying stars, have a way of capturing our imagination. They were once just theoretical predictions, but over the years, astronomers have uncovered more and more evidence that black holes are very real, and they're scattered throughout our universe. These cosmic giants form when massive stars run out of fuel and collapse under their own gravity, compressing all their matter into a single point known as a singularity. The singularity is a place of infinite density and gravity, so intense that all matter is crushed into an unimaginably small space. Around this point lies the event horizon, a boundary where gravity is so strong that not even light can escape. Beyond the event horizon, scientists can only speculate on what truly happens. Some suggest that everything that falls into a black hole is compressed to a single point, crushed to an infinite density at the singularity. Others believe that black holes might be connected to wormholes that lead to other parts of the universe, or even to different universes altogether. All we know is that once something crosses that invisible line, it's beyond our reach. Once anything crosses the event horizon, whether it's a beam of light, a planet, or even a star, it's lost forever. Our best scientific theories, like Einstein's theory of relativity, explain how gravity works on a large scale and predict the formation of black holes. But when it comes to the singularity, these theories start to fall apart. At this level, our understanding of physics breaks down completely, and the usual laws of nature no longer apply. It's as if black holes exist as a kind of wall in our knowledge. Black holes come in various sizes, from stellar black holes, a few times more massive than our sun, to supermassive black holes that weigh billions of times more. These supermassive giants sit at the heart of galaxies, shaping the lives of stars and planets around them. Black holes can feed on nearby stars and matter, growing larger and more powerful over time. Stellar black holes, though only one type in the wide spectrum of black holes, are some of the most iconic and well-studied. When a massive star, one with at least 8 times the mass of our sun, reaches the end of its life, it undergoes a transformation that's as violent as it is final. For millions of years, these stars burn hot and bright, fusing hydrogen into helium and then into heavier elements, with the force of nuclear fusion pushing outwards against the force of gravity. But eventually, they reach a point where they can no longer sustain this fusion process. With no more fuel to burn, the outward pressure disappears and gravity takes over completely. The core collapses inward under its own weight, and in a fraction of a second, it becomes so dense that a black hole is born, and the rest of the star is blown outward in an explosion called a supernova that can briefly outshine entire galaxies. But what's left behind is a darkness so powerful that nothing can escape it. The newly formed black hole may start small, but as it consumes nearby gas, dust, and sometimes even entire stars, it grows, becoming more massive and increasing the size of its event horizon. These stellar black holes vary in size, but they generally contain about 3 to 10 times the mass of our sun. Even though they are relatively small compared to supermassive black holes, their gravitational pull is still powerful and far-reaching. In some cases, stellar black holes exist alone in space, unnoticed and undetectable, without any nearby material to reveal their presence. But in other cases, a stellar black hole has a partner, a nearby star that it orbits. When a black hole and a star orbit each other, the immense gravity of the black hole can start to pull matter off the star. This material spirals inward, forming an accretion disk, a swirling, glowing ring of gas and dust that heats up to extreme temperatures as it approaches the black hole. From a distance, these systems appear as bright X-ray sources, which can be detected by telescopes here on Earth. Observing these X-rays allows scientists to study the black hole's behavior and even estimate its mass. These X-ray binaries, as they're called, are some of the best evidence we have for the existence of stellar black holes. The intense light they produce reveals details about the speed and pattern of the material spiraling inward, which in turn provides insights into the physics of the black hole itself. The intense gravity of a stellar black hole creates a gravitational well in space, bending the paths of nearby objects. A planet orbiting close to a black hole would experience strong gravitational tides, stretching and squeezing as it moved through the uneven gravitational field. If a planet ventured too close, it could be torn apart entirely, its debris spiraling into the black hole in a final, violent encounter. Fortunately, such events are rare, and most stellar black holes drift through space far from any potential victims. In some galaxies, stellar black holes are scattered throughout the arms and disks, hidden among billions of stars. Their influence on their galactic neighborhoods may be small, but each one represents the endpoint of a massive star's life, a kind of cosmic gravestone marking where a sun once burned bright. Stellar black holes remain largely the same size as when they formed. This makes them stable, enduring objects that can drift through space unchanged for eons, holding on to the secrets of their formation. In the vast expanse of space, some stellar black holes may even drift alone, completely undetectable. These quiet black holes pose a special challenge to astronomers because, without an accretion disk or a partner star, they don't produce any detectable radiation. They are truly invisible, their presence inferred only by their gravitational effects or, in some cases, by the bending of light from distant stars behind them. This phenomenon, known as gravitational lensing, occurs when a black hole passes between us and a distant star, acting like a magnifying glass and distorting the star's light. By observing these distortions, scientists can sometimes infer the presence of a stellar black hole even if it is otherwise hidden. In some cases, stellar black holes can merge with each other or with neutron stars, creating gravitational waves that ripple across space. These waves, first detected in 2015, have opened up a new way of studying the cosmos, allowing scientists to observe collisions between black holes directly. Each merger is like a seismic event in space, a brief but powerful release of energy that echoes across the universe. These mergers are rare, but when they happen, they offer a unique opportunity to learn about black hole properties, such as their mass and spin. Intermediate black holes, the missing links of the universe, occupy a unique space in the black hole family. These black holes are neither as small as stellar black holes, nor as massive as the supermassive black holes that lie at the centers of galaxies. Instead, they sit in between, with masses ranging from hundreds to thousands of times that of our Sun. Despite their predicted existence, finding and studying intermediate black holes has proven to be incredibly challenging. If intermediate black holes do exist, they might act as stepping stones between small stellar black holes and the massive giants that dominate the centers of galaxies. The idea is that, over time, smaller black holes could merge or gather enough material to grow into intermediate sizes, which might eventually lead to the formation of supermassive black holes. But if that's the case, why are they so hard to find? Shouldn't the universe be full of these mid-sized black holes, especially in the bustling areas of space where galaxies collide or where many stars are packed together? One of the biggest challenges in finding intermediate black holes is that they are not as active as their larger counterparts. Supermassive black holes often have huge accretion disks of gas and dust swirling around them, emitting vast amounts of light and energy that make them visible even across large distances. But intermediate black holes, especially if they are isolated or in quieter parts of space, might not have enough surrounding material to create the same type of brilliant display. Without an accretion disk or bright X-ray signals, an intermediate black hole would be almost invisible, blending into the background of space and eluding our telescopes. However, there are some indirect ways to detect these elusive objects. One of the primary methods is by looking for gravitational effects. When an intermediate black hole passes near a star or a cloud of gas, its gravity can cause subtle shifts in the objects around it. Astronomers can sometimes spot these disturbances by watching for changes in the orbits of stars or the shape of gas clouds. Another method involves looking for gravitational waves that are produced when black holes merge. If a stellar black hole were to collide with an intermediate black hole, the event would create gravitational waves strong enough to be detected by observatories on Earth. These waves would offer hints about the sizes and locations of intermediate black holes, even if we can't see them directly. Despite the difficulty in detecting them, there have been a few promising candidates for intermediate black holes. One well-known case is a black hole found in the dense star cluster known as Omega Centauri, located in our own galaxy. This cluster contains hundreds of thousands of stars packed tightly together, making it a prime location for black holes to form. Some observations have suggested that Omega Centauri may contain an intermediate black hole several thousand times the mass of our Sun at its center, exerting gravitational influence on the surrounding stars. While the evidence isn't conclusive, it gives scientists hope that intermediate black holes might be lurking in other similar star clusters. In the galaxy M82, astronomers observed a powerful X-ray source that appeared too bright to be caused by a stellar black hole, but was too small to be a supermassive black hole. This object, named M82X1, could be an intermediate black hole, shining brightly as it consumes material from a nearby star. The clearest evidence, however, comes from GW190521, a gravitational wave signal from 2019, which indicated that about 17 billion light-years away, an 85 solar mass black hole had merged with one that was 66 solar masses, resulting in the formation of a 142 solar mass black hole. This new black hole was about 9 solar masses smaller than the combination of the two because that mass was released as energy in the form of gravitational waves. The importance of intermediate black holes goes beyond simply filling in the gaps in black hole sizes. These mid-sized objects could play a crucial role in shaping galaxies. If intermediate black holes exist in the centers of star clusters or small galaxies, they could help to merge and organize the surrounding stars, contributing to the overall structure of galaxies. When galaxies collide, intermediate black holes from each galaxy could eventually find each other, merging and potentially leading to the formation of a supermassive black hole in the merged galaxy's center. The process of galaxy formation and evolution is still a major mystery in astrophysics, and intermediate black holes might be one of the missing pieces. If these black holes were more common in the early universe, they could have provided the seeds for today's supermassive black holes. The early universe was a chaotic place, full of young massive stars and dense gas clouds that could have easily created intermediate black holes through frequent collisions and star deaths. Over billions of years, these intermediate black holes could have grown by consuming gas and merging with each other, gradually forming the supermassive black holes we see today. Supermassive black holes, giants of the galactic core, are the true giants of the universe. They dominate the centers of galaxies, including our own Milky Way. These enormous black holes can weigh millions or even billions of times more than our Sun. Their sheer size and power make them some of the most influential objects in the cosmos, not just for their gravity, but for the way they shape entire galaxies and help us understand the broader story of cosmic evolution. Every large galaxy that astronomers have studied in detail seems to have a supermassive black hole at its core. The connection between galaxies and their central black holes runs deep, and while much of it remains a mystery, scientists are beginning to piece together the role these supermassive objects play in the universe. The most well-known supermassive black hole is Sagittarius A*, SGR A*, located at the heart of the Milky Way. This enormous black hole is about 4 million times the mass of the Sun, but it is surprisingly quiet compared to some of its more active counterparts in other galaxies. Unlike quasars or active galactic nuclei, which are supermassive black holes surrounded by huge, glowing accretion disks. SGRA asterisk has relatively little material falling into it. As a result, it emits very little light and is difficult to observe directly. However, astronomers have been able to study its influence by observing the orbits of stars near the galactic center. These stars move at incredible speeds, their paths curved by the immense gravity of SGRA asterisk, providing conclusive evidence of the black hole's existence. While supermassive black holes like SGRA asterisk may be relatively quiet, others are far more active and dramatic. In galaxies known as quasars, the central black hole is surrounded by an enormous accretion disk of gas, dust, and other material spiraling inward at incredible speeds. As this material falls into the black hole, it heats up to millions of degrees, emitting vast amounts of energy across the electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. These brilliant displays can outshine entire galaxies, making quasars some of the brightest and most distant objects in the universe. In the case of the Milky Way, astronomers believe that SGRA asterisk was likely more active in the past. Evidence from X-ray observations and other studies suggests that the central black hole may have undergone periods of high activity, consuming large amounts of material and emitting powerful jets of energy. These episodes of activity could have influenced the surrounding stars and gas, shaping the structure of the galaxy. Even though SGRA asterisk is relatively quiet now, it remains an important focus of research as it provides a nearby example of a supermassive black hole that scientists can study in detail. The relationship between galaxies and their supermassive black holes is one of the most intriguing areas of modern astronomy. For reasons that are not yet fully understood, the mass of a galaxy's central black hole is closely correlated with the properties of the galaxy itself, such as the size of its bulge and the speed of its stars. This correlation, known as the black hole-galaxy connection, suggests that supermassive black holes and galaxies evolved together, influencing each other over time. One theory is that the energy released by supermassive black holes during periods of high activity can regulate star formation in their host galaxies. For example, powerful jets of energy from an active black hole could heat up or blow away gas clouds, preventing them from collapsing to form new stars. This process, known as feedback, could help to explain why some galaxies are filled with young, hot stars, while others are more quiescent and filled with older, cooler stars. As we study more supermassive black holes and their host galaxies, we are learning that these giants are not just passive objects sitting at the centers of galaxies. Instead, they play a dynamic role in shaping the evolution of the cosmos, influencing everything from the formation of stars to the distribution of matter on the largest scales. The formation of supermassive black holes remains one of the great unsolved mysteries of astronomy. While stellar black holes form from the collapse of massive stars, the origins of supermassive black holes are far less clear. One possibility is that they grew gradually over billions of years, starting as smaller black holes that merged with other black holes or consumed large amounts of gas and dust. Another theory is that supermassive black holes formed directly from the collapse of enormous clouds of gas in the early universe, bypassing the intermediate stages entirely. Recent discoveries have shown that some supermassive black holes existed when the universe was less than 1 billion years old, which is far earlier than previously thought. These early black holes challenge our understanding of how such massive objects could have formed so quickly. They may hold the key to understanding the conditions of the early universe and the processes that shaped the cosmos as we see it today. While stellar black holes and supermassive black holes are the most well-known types, the universe also contains a strange and elusive class of black holes known as phantom black holes. These theoretical objects represent the possibility that some black holes could exist without forming from stars or other normal matter. Instead, phantom black holes might be made entirely of dark matter, the mysterious and invisible substance that makes up most of the mass in the universe. Dark matter doesn't interact with light or normal matter in the same way, so if a black hole were made of dark matter, it might be almost impossible to detect. These phantom black holes could be lurking in the vast emptiness of space, influencing the movement of galaxies and stars, but leaving no other trace of their presence. Some scientists speculate that phantom black holes could help to explain some of the unexplained phenomena in the universe, such as the unusual motions of stars in distant galaxies or the way gravity behaves on the largest scales. While they remain purely theoretical for now, phantom black holes are a reminder of how much we still have to learn about the universe and the mysterious forces that shape it. To understand how these phantom black holes might form, we need to delve into the nature of dark matter itself. Dark matter is believed to be a type of particle that interacts only through gravity and possibly through the weak nuclear force. It doesn't emit or absorb light, which makes it invisible to telescopes. If dark matter particles could somehow clump together and collapse under their own gravity, they might form black holes that are made entirely of dark matter. These phantom black holes would be fundamentally different from the ones we know, and they might behave in ways that challenge our current understanding of physics. Phantom black holes might also offer clues about the nature of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Some theories suggest that dark energy and dark matter are connected, and that understanding one could help to unravel the mystery of the other. If phantom black holes are real, they could be the missing link that ties these two enigmatic forces together, offering a new way to explore the fundamental laws of the universe. This M87 black hole was also the first ever black hole to be imaged in 2019 through data gathered from the Event Horizon Telescope. Despite their incredible mass, supermassive black holes don't simply sit at the centers of galaxies without influence. Instead, they play an active role in shaping the structures of the galaxies around them. One of the ways they do this is by controlling the flow of gas and stars in their neighborhoods. Because of their intense gravitational pull, they can gather material from their surroundings, creating accretion disks that can glow so brightly that they outshine entire galaxies, creating what astronomers call active galactic nuclei (AGNs). When viewed from far away, an active galaxy looks like a single bright spot, with jets of radiation streaming from its center, a sign that its supermassive black hole is actively consuming material. These jets are some of the most powerful features associated with supermassive black holes. As material falls toward the black hole and heats up, some of it is expelled in two opposite directions, forming jets that travel at nearly the speed of light. These jets can extend for thousands of light years, pushing through the surrounding galaxy and even beyond into intergalactic space. The force of these jets is so intense that it can clear out gas from large regions of the galaxy, halting star formation in those areas. In this way, supermassive black holes act as regulators of galactic growth, controlling how much gas is available for new stars and shaping the distribution of stars within the galaxy. Some theories suggest that galaxies and their central black holes grow together, influencing each other over billions of years. When a galaxy is young and filled with gas, it can produce new stars at a rapid rate. But as the central black hole grows, its jets and radiation start to heat up and blow away the surrounding gas, gradually slowing down star formation. This feedback loop could be what allows galaxies to reach a stable size, with the black hole acting as a kind of galactic thermostat, preventing runaway growth. The exact process by which supermassive black holes form is still one of the biggest mysteries in astrophysics. There are a few leading theories, but none have been fully confirmed. One idea is that these black holes grew from the merger of many smaller black holes over time, a process that could have started in the very early universe when the first stars and galaxies were forming. Another theory is that supermassive black holes formed directly from massive clouds of gas that collapsed under their own gravity, creating a black hole from scratch without the need for a star. This second theory is particularly intriguing because it suggests that some black holes may have existed in the early universe, even before the first stars had a chance to explode and create stellar black holes. By studying the light from distant quasars, galaxies with extremely bright active nuclei, we can see supermassive black holes as they appeared billions of years ago, back when the universe was young. These quasars allow us to trace the history of black holes and galaxies, helping us understand how structures formed and evolved over time. Some quasars are so far away that the light we see from them today began its journey across the universe when the universe itself was only a fraction of its current age. Ultramassive black holes. When supermassive just isn't enough. When it comes to black holes, the word supermassive might seem like the ultimate descriptor, but in the cosmos, there are a few black holes that go beyond even that category. These rare, extraordinary entities, known as ultramassive black holes, stretch the boundaries of what we understand about mass, gravity, and the formation of cosmic structures. Ultramassive black holes are defined as black holes with masses exceeding 5 billion times that of our Sun, and in some cases, they reach 50 billion solar masses or more. The scale of these objects is almost unimaginable, and they challenge astronomers to rethink not only the upper limits of black hole mass, but also how such behemoths could form in the first place. One of the first questions that arise when considering ultramassive black holes is, how do they grow to such astonishing sizes? For black holes of this mass, the typical growth methods we know of, merging with other black holes or gradually accumulating gas from the galaxy around them, are not quite sufficient to explain their sheer size. Mergers between black holes are rare and occur over incredibly long timescales, so accumulating billions of solar masses in this way would take far longer than the age of the universe. Similarly, the material in a galaxy is finite, meaning that even if an ultramassive black hole were to consume gas and dust at a steady rate, it still wouldn't grow quickly enough to reach these immense sizes within the lifespan of the universe. Some scientists theorize that ultramassive black holes may have had a head start in the early universe. According to one hypothesis, these colossal black holes may have started as primordial black holes formed shortly after the Big Bang, when the universe was much denser and more chaotic. If such primordial black holes existed, they could have grown rapidly by consuming large amounts of gas in the early universe, allowing them to reach ultramassive sizes within a relatively short period. Another possibility is that ultramassive black holes are the result of extreme galactic mergers. When two large galaxies collide, their central black holes often merge as well. In rare cases, multiple mergers involving galaxies that each contain supermassive black holes might lead to the creation of an ultramassive black hole. These events are rare, and for an ultramassive black hole to form, the conditions would need to be just right. A series of galaxy collisions, each one adding to the central black hole's mass, might allow a black hole to grow to an ultramassive size over billions of years. These ultramassive black holes would be found in the largest galaxies and galaxy clusters, where the environment is dense enough to support such growth. Currently, only a few ultramassive black holes have been detected, and they tend to exist in the most massive and densely populated regions of the universe. One well-known example is the black hole TON 618, located in a galaxy about 11 billion light-years from Earth. TON 618 is estimated to have a mass of around 40.7 billion solar masses, making it one of the largest black holes ever discovered. Since it is an active galactic nucleus, it emits a great deal of light. So much so, in fact, that the surrounding galaxy is outshone by it and hence is not visible to us. It is 140 trillion times brighter than our Sun, making it one of the brightest known objects in the universe. We know that black holes feed on surrounding matter, pulling in gas and dust as they grow. However, if a black hole becomes too massive, it can actually begin to interfere with its own growth. The intense energy released as gas falls into the black hole heats up and pushes material away, creating a feedback effect. This feedback can drive gas away from the center of the galaxy, limiting the amount of material that can fall into the black hole. This effect is so powerful that it's often thought to be responsible for limiting the size of supermassive black holes. But ultramassive black holes suggest that, somehow, a few black holes have managed to overcome this limit and keep growing, defying the feedback process that usually restricts their size. The effects of ultramassive black holes extend far beyond their immediate surroundings. Because of their mass, they have an enormous gravitational reach, influencing stars, gas, and even other galaxies and galaxy clusters. The presence of an ultramassive black hole at the center can shape the behavior of nearby galaxies. The black hole's powerful gravitational pull can hold the cluster together, preventing galaxies from drifting away and keeping the cluster's structure intact. Ultramassive black holes also produce massive jets of energy, similar to supermassive black holes, but on an even grander scale. These jets can extend far beyond the galaxy, heating gas in the surrounding area and affecting star formation in neighboring galaxies. In this way, ultramassive black holes act as cosmic architects, helping to shape the structure and evolution of galaxy clusters. As we develop more powerful telescopes and observatories, our ability to detect and study ultramassive black holes is expected to improve. Future missions may allow us to see these giants in greater detail, observing their interactions with surrounding galaxies and the effects of their immense gravitational fields. Primordial black holes, ghosts from the dawn of the universe. Unlike black holes that form from the collapse of massive stars, primordial black holes are believed to have formed in the earliest seconds of the universe, created directly from the extreme conditions of the early cosmos. At that time, the universe was incredibly compact, with energy and matter packed so tightly that tiny fluctuations in density could have led to areas with enough gravitational pull to collapse in on themselves, forming black holes. These hypothetical black holes, known as primordial black holes, would have been born without needing stars, existing as relics from a period long before galaxies, stars, or even atoms as we know them came into being. Primordial black holes offer a potential answer to some of the universe's biggest mysteries. One of these mysteries is the origin of dark matter. Dark matter is a form of matter that does not emit light, making it invisible and undetectable by conventional telescopes. Scientists know that dark matter exists because its gravitational influence can be seen affecting galaxies and galaxy clusters. Without dark matter, galaxies would lack the mass needed to hold their stars together, and entire galaxy clusters would lack the gravitational glue needed to bind them. But despite decades of study, scientists have yet to identify what dark matter is made of. Some scientists think primordial black holes might be a solution to the dark matter mystery. If a large number of these black holes formed in the early universe, they could be scattered throughout the cosmos, creating a network of dark objects that exert gravitational forces on visible matter. Unlike the regular matter that makes up stars, planets, and galaxies, these primordial black holes wouldn't emit any light. They would be, in effect, dark objects, matching the behavior of dark matter. If primordial black holes do exist and make up a significant portion of dark matter, it would mean that dark matter isn't made of exotic particles, as many scientists have previously assumed, but instead of ancient black holes left over from the early universe. Primordial black holes would be much smaller than the black holes we are used to thinking about, possibly with masses ranging from that of a small asteroid to several times the mass of the Sun. Unlike larger black holes, which influence their surroundings by pulling in nearby gas and dust, smaller primordial black holes would be nearly invisible, interacting only through their gravitational pull. This makes them challenging to observe directly. However, there are some ways to infer their presence. For instance, scientists can search for tiny distortions in the light from distant stars, indicating the gravitational influence of a small, invisible black hole passing in front of them. This technique, known as gravitational microlensing, can reveal the presence of compact objects that would otherwise go unnoticed. In the early universe, matter was distributed more or less evenly, but slight irregularities eventually led to the clumping of gas, which formed the first stars and galaxies. The presence of primordial black holes could have acted as seeds for these structures, providing gravitational centers around which matter could gather. Over time, these seeds would have attracted more gas and dust, leading to the birth of stars and galaxies. In this way, primordial black holes could have helped shape the universe as we know it, guiding the formation of the first galaxies and setting the stage for the cosmic landscape we observe today. Without some kind of seed to initiate the formation of galaxies, It's difficult to understand how cosmic structures could have emerged as quickly as they did after the Big Bang. If primordial black holes were present, they would have acted as catalysts, providing the gravitational anchor points needed to draw in matter and accelerate the process of galaxy formation. This theory aligns with observations showing that galaxies began forming relatively soon after the Big Bang, suggesting that some kind of gravitational scaffolding may have been in place to guide their development. But while primordial black holes offer fascinating explanations for dark matter and galaxy formation, their existence remains hypothetical. The search for primordial black holes has led scientists to explore a variety of methods, from gravitational wave detectors to cosmic microwave background studies. Gravitational wave observatories like LIGO and Virgo, which have already detected mergers between larger black holes, could potentially pick up signals from merging primordial black holes as well. However, such events would likely be much rarer and fainter than those produced by larger black holes. Scientists are also studying the cosmic microwave background, the faint glow of radiation left over from the Big Bang. If primordial black holes were abundant in the early universe, they could have left subtle imprints on this background radiation, altering its structure in ways that might still be detectable today. Rogue black holes. Wandering dangers in the galactic void. Rogue black holes are not bound to any specific location, but move through the galaxy with little regard for what lies in their path. These objects, though potentially smaller in scale than their supermassive counterparts, are nevertheless capable of decimating anything that crosses their trajectory. Stars, planets, even entire solar systems could face disruption if one of these rogue black holes were to drift close enough. Rogue black holes are thought to form when a black hole gets ejected from its home galaxy or star cluster, often as a result of powerful gravitational interactions. One common cause of such an ejection is the merger of two black holes. When two black holes come together, the final merger can release intense gravitational waves that carry energy away from the system. This loss of energy can send the resulting black hole hurtling in a random direction, effectively ejecting it from its original location. Another possible cause is when a black hole forms from a star that is part of a binary system. If one star collapses into a black hole while the other remains intact, the gravitational relationship between the two might break, sending the black hole on a wandering journey through space. Once a black hole is on the move, its journey is governed by the natural orbits and motions of galaxies and star clusters. Some rogue black holes may eventually find new homes, settling into orbits around other stars or entering different star clusters. Others, however, may wander for billions of years without encountering anything substantial. In the vastness of space, it's entirely possible for a rogue black hole to travel undisturbed through interstellar space, far from stars, planets, or other celestial bodies. But on occasion, a rogue black hole could stray close to a solar system, disrupting or even destroying any planets or stars within range. If a rogue black hole were to enter our solar system, the results could be devastating. The black hole's gravity would cause major disturbances, potentially altering the orbits of planets or drawing gas and dust from nearby stars. For a black hole that's only a few times the mass of our Sun, such an encounter might start with distant gravitational effects, with the outer planets experiencing changes in their orbits. But as the black hole gets closer, its influence would grow stronger, and eventually, it could reach a point where planets are pulled from their paths altogether or even swallowed by the black hole. For a system like ours, a rogue black hole would be a serious threat, even if it never came close enough to Earth. The disruption to the gravitational balance would throw planets, asteroids, and other bodies into new, unpredictable paths, causing chaos on a cosmic scale. One of the most unsettling aspects of rogue black holes is their stealth. Unlike stars, which emit light, black holes are nearly invisible. They don't radiate light or other forms of electromagnetic energy, making them difficult to detect unless they interact with nearby matter. The only way we'd notice it is if it began to pull on the system with its gravity, causing stars or planets to shift in their orbits. In cases where rogue black holes are actively consuming matter, they may become detected. As a black hole feeds on gas or dust, this material can form an accretion disk around the black hole, heating up and emitting light as it spirals inward. But in the emptiness of interstellar space, where there is often little or no material to consume, a rogue black hole could remain entirely undetectable until it comes disturbingly close. Astronomers believe there may be millions of rogue black holes scattered throughout our galaxy, but spotting them is challenging. Some methods, like gravitational microlensing, have been used to detect a few potential rogue black holes, but it requires precise alignment and timing. The vastness of space means that the chances of a rogue black hole crossing paths with a populated star system are low, but the possibility is there. Hyperenergetic quasars, unleashing black hole fury across the cosmos. Quasars are among the most powerful and luminous objects in the universe, so brilliant they can outshine entire galaxies. They are born from supermassive black holes that are actively consuming enormous amounts of material. This relentless consumption fuels a process that transforms these black holes into cosmic beacons, illuminating the dark depths of space with intense energy. The material falling toward the black hole first forms an accretion disk. As this material spirals inward, it gets compressed and heated to extreme temperatures, releasing vast amounts of light and other forms of energy. This energy is what makes quasars so bright. In some cases, a single quasar can shine hundreds of times brighter than an entire galaxy, allowing astronomers to observe them from billions of light years away. The intense brightness of quasars isn't just due to visible light. They emit energy across nearly the entire electromagnetic spectrum, from radio waves to X-rays and even gamma rays. This wide range of energy output makes quasars visible to different types of telescopes, each capturing different parts of the radiation they emit. This broad energy range shows that quasars are not just bright, but also incredibly energetic, releasing more power in a single second than our sun will emit over billions of years. Quasars often generate powerful jets that shoot out from their poles. These jets are made up of charged particles accelerated to nearly the speed of light, and they can extend for hundreds of thousands, even millions of light years beyond the host galaxy. The energy carried by these jets interacts with gas, dust, and other galaxies in the surrounding region, creating shock waves and influencing the evolution of galaxies nearby. The jets can be powerful enough to push material out of the galaxy, halting star formation by removing the gas needed to form new stars. The jets from a quasar can also heat up intergalactic gas, preventing it from cooling and collapsing to form stars. In this way, quasars can suppress star formation not only in their own host galaxies, but also in nearby galaxies, effectively sterilizing parts of the universe. Because they are so bright, quasars can be observed across vast distances, allowing scientists to look back billions of years in time. The light we see from distant quasars began its journey long before our sun or solar system even existed, providing a direct window into the early universe. By studying quasars at different distances, astronomers can trace the evolution of galaxies and black holes over cosmic history, piecing together how the first black holes formed, grew, and influenced their surroundings. While quasars are mostly observed in distant galaxies, there was a time when they were more common in the universe. In the early stages of the universe, galaxies were closer together and full of gas, creating the ideal conditions for black holes to feed and generate quasars. Over time, as galaxies evolved and their central black holes consumed nearby material, quasars became less common, giving way to quieter galaxies like our own Milky Way. Today, most quasars we observe are billions of light years away, meaning we're seeing them as they were in the distant past. If a quasar were to flare up in a galaxy relatively close to ours, the intense radiation could have serious consequences for nearby star systems, potentially even affecting planets. The gamma rays and other high-energy radiation emitted by quasars could strip away atmospheres or disrupt the chemical processes necessary for life. Fortunately, most active quasars are far from our galaxy. The amount of material required to fuel a quasar is immense, raising questions about how such large amounts of gas and dust accumulate and feed the black hole over time. The physics of the jets produced by quasars also remains an area of active research, as scientists try to understand how particles are accelerated to such extreme speeds and what role magnetic fields play in the process. Quasars serve as powerful examples of how black holes, despite their name, can be some of the brightest and most dynamic objects in the universe. What sets blazars apart is the alignment of their powerful jets, which are directed almost precisely toward Earth. This alignment makes blazars appear especially bright to observers on Earth. This direct line-of-sight alignment allows us to see details of their energetic processes that are hidden in other galaxies. The intense brightness of blazars comes from the supermassive black hole at their core, which pulls in massive amounts of gas and dust from the galaxy around it. But it's the jets streaming from the poles of the black hole that make blazars so remarkable. These jets are composed of charged particles, like electrons, accelerated to near the speed of light by powerful magnetic fields generated by the black hole's spin. As these jets point directly at Earth, they become concentrated and amplified, creating what scientists call a relativistic beaming effect. This effect is like shining a flashlight directly into an observer's eyes. It makes the blazar appear brighter and more energetic than it would if the jet were oriented away from us. These powerful jets emit radiation across the entire electromagnetic spectrum, producing waves of energy that can be detected by various types of telescopes, including radio, optical, and gamma-ray observatories. The energy output of blazars is so great that they can fluctuate rapidly, with bursts and flares that vary in brightness from day to day or even minute to minute. These flares are driven by turbulence and collisions within the jet, as particles slam into each other and release energy. The cause of these eruptions is still not entirely understood, but they likely involve sudden shifts in the magnetic fields surrounding the black hole, leading to explosions of energy that send powerful waves of radiation toward Earth. The radiation emitted by blazars includes gamma rays, the most energetic form of light. Gamma rays are dangerous because they have enough energy to penetrate matter and disrupt atoms, breaking apart molecules and creating harmful particles. When blazars flare up, they send streams of gamma rays into space. If Earth were close enough to an active blazar, the radiation could have serious effects on our planet, stripping away parts of the atmosphere or disrupting life by interfering with biological processes. Fortunately, the nearest known blazars are far enough away that their gamma rays disperse and weaken long before reaching us. However, studying the impact of this intense radiation allows scientists to understand the potential hazards that similar processes could pose if they occurred closer to home. Blazars don't just emit light. They also send out high-energy particles known as cosmic rays. These cosmic rays, accelerated to incredible speeds by the magnetic fields in the jets, are some of the fastest-moving particles in the universe. When they reach Earth, they collide with particles in our atmosphere, creating showers of secondary particles that can be detected on the ground. Cosmic rays from blazars provide valuable information about the composition and behavior of the jets. However, cosmic rays are also a form of radiation that, in high doses, can be harmful. The brightness and variability of blazars make them ideal natural laboratories for studying high-energy physics, helping researchers refine models of how black holes interact with their surroundings. Black holes come from observations of the centers of galaxies, where a supermassive black hole should be present, yet appears to be missing. In these cases, astronomers speculate that the black hole was ejected after a merger. In a few cases, scientists have spotted strange luminous trails, thought to be recoiling black holes pulling along a stream of gas or stars as they leave their galaxies behind. Depending on the strength of the gravitational wave kick, a recoiling black hole could travel through space at speeds of thousands of kilometers per second. This velocity is fast enough to escape not only the core of the galaxy, but even its outer regions. Once it escapes, the black hole is left to drift through intergalactic space. There, The recoiling black hole would likely continue to pull in any gas or dust it encounters, but without the rich environment of a galaxy, it would appear mostly invisible, nearly impossible to detect directly. Without a central black hole, the galaxy loses a powerful gravitational anchor. This can lead to changes in the movement of stars, as well as the distribution of gas and dust, ultimately affecting the galaxy's future shape and development. In some cases, the galaxy may eventually attract another black hole, but until then, it may lack the typical features of a galaxy with an active central supermassive black hole. The rarity of these events means that recoiling black holes are difficult to study, and so far, astronomers have only indirect evidence of their existence. What happens to these black holes over long stretches of time? Do they eventually slow down or settle into new locations? Could they influence the formation of new galaxies, or will they remain as isolated points of intense gravity in the emptiness of space? X-ray beacons of doom. Black holes as powerful cosmic lighthouses. Some black holes become powerful sources of X-ray emissions, illuminating the dark cosmos with radiation that travels across vast distances. These X-ray beacons can be incredibly intense, providing a way for astronomers to detect black holes that would otherwise be invisible. These X-rays are produced when friction and immense pressure within the accretion disk generate extreme heat, sometimes reaching millions of degrees. At these temperatures, the material emits X-rays, which stream outward from the black hole and into space. One of the most famous examples of a black hole X-ray source is Cygnus X1, a stellar mass black hole about 7,200 light-years from Earth in the constellation Cygnus. Cygnus X1 is locked in a gravitational dance with a nearby star, drawing gas from its companion into an accretion disk. The disk heats up and produces an intense stream of X-rays that astronomers have been observing since the 1960s. In binary systems, where a black hole and a star orbit each other, the intense X-rays can strip material away from the companion star, altering its evolution over time. This radiation can erode the outer layers of the star, disrupting its surface and possibly changing its fate. The star may age faster or evolve differently than it would have without the influence of the black hole's radiation, creating a strange symbiotic relationship where the black hole's presence shapes the life of its neighboring star. For any nearby planets, the intense X-rays from a black hole would be devastating. X-rays are a form of high-energy radiation, and prolonged exposure can strip away planetary atmospheres, especially if the planet orbits close to the black hole. The radiation could also interfere with any chemical processes essential to life. Even if a planet were located at a safer distance, occasional flares from the black hole's accretion disk could create bursts of radiation strong enough to impact any organisms living on its surface. X-ray emissions from black holes can also be detected over large cosmic distances. Supermassive black holes often produce intense X-rays, which allow astronomers to detect and study them from billions of light-years away. Quasars emit vast amounts of energy across the electromagnetic spectrum, including X-rays. This radiation allows astronomers to detect quasars in distant galaxies, serving as a kind of cosmic lighthouse that illuminates the far reaches of space. X-ray observations of black holes have opened up new ways to study these jets and understand their effects. In many ways, X-ray emissions provide a snapshot of the activity happening near the black hole, capturing the release of energy and its journey through space. This gives scientists a valuable window into the high-energy physics of black holes and the forces that shape galaxies. By studying X-rays, scientists can learn about the size, mass, and even the spin of a black hole. The intensity and variability of the X-ray emissions can reveal details about the black hole's accretion disk, the amount of matter it's consuming, and the behavior of the surrounding gas. In some cases, astronomers can detect quasi-periodic oscillations, QPOs, in the X-ray emissions, which are thought to be caused by matter orbiting close to the black hole's event horizon. X-ray astronomy has grown tremendously in recent decades, allowing scientists to uncover more about the nature of black holes. Observatories like the Chandra X-ray Observatory and the European Space Agency's XMM Newton telescope have played a crucial role in advancing our understanding of these cosmic phenomena. With the ability to detect X-ray emissions across different wavelengths, these telescopes allow astronomers to explore black holes in greater detail, uncovering mysteries that were once beyond our reach. Despite the dangers associated with X-ray emissions from black holes, these signals are essential for advancing our knowledge of the universe. Without X-rays, many black holes would remain hidden, and we would know far less about their role in cosmic evolution. Black holes' mass is so enormous that it alters the orbits of stars millions of times farther out, essentially controlling the gravitational structure of the entire galaxy. The Event Horizon Telescope is not a single telescope, but rather a global network of radio telescopes spread across the planet. These telescopes, located at sites like Hawaii, Mexico, Antarctica, and Spain, combine their observations through a technique known as Very Long Baseline Interferometry, VLEI. By linking up telescopes across Earth, scientists effectively created a planet-sized telescope capable of capturing details at an unprecedented level of precision. Each telescope in the network collects radio waves emitted by M87*, gathering data across vast distances to build a detailed picture. The black hole's incredible distance from Earth would make it seem nearly impossible to observe in such detail, but VLEI allowed scientists to achieve the necessary resolution. This process required algorithms that could fill in gaps in data, essentially reconstructing the final image from incomplete signals. The resulting image of M87* wasn't sharp in the way we might expect from a photograph. Instead, it was a hazy glowing ring encircling a dark core. This dark center is the shadow of the black hole, the spot where gravity is so strong that even light cannot escape. The glowing ring is created by gas and dust heated to extreme temperatures as they swirl around the black hole, close to the event horizon. It's here on this edge that light is bent by gravitational forces so intense that it creates a ring-like appearance. General relativity predicted the shape and structure of the event horizon's shadow, and the actual image of M87* aligned remarkably well with these predictions. The dark center, surrounded by the ring of light, fit the theoretical models almost precisely. For physicists, this was a significant moment, an observational confirmation that general relativity still held up, even in the most extreme environments we can imagine. M87* is a particularly active black hole, meaning it feeds on a steady supply of matter drawn from its surroundings. The swirling gas and dust around M87* emit massive amounts of energy, and some of this material is funneled into jets that shoot out from the poles of the black hole. The jets from M87* are among the most powerful known, capable of shaping the surrounding galaxy by blasting material outward, influencing star formation, and altering the distribution of gas within M87 itself. The material around M87* doesn't just spin in random directions. It forms an accretion disk that is closely aligned with the direction of the jets. By studying these jets and their orientation, astronomers can determine the black hole's rotation and gain insights into how M87* interacts with the galaxy. The fact that M87* produces jets at all suggests it's a rapidly spinning black hole, as the rotation of the black hole's magnetic field likely plays a role in driving the jets. The EHD project involved hundreds of scientists, engineers, and institutions from around the world, each contributing expertise, resources, and time. It took years to coordinate the telescopes, process the data, and reconstruct the image. In fact, the amount of data collected by the EHD was so vast that it couldn't be transmitted digitally. Instead, hard drives were flown across the world to be analyzed. A black hole consuming its own galaxy, the tail of NGC 4889. In the distant Coma cluster lies a massive elliptical galaxy named NGC 4889, home to one of the largest black holes known to astronomers. This supermassive black hole, hidden within the center of NGC 4889, has a mass estimated to be around 21 billion times that of the Sun, about 3 to 6 times larger than the humongous M87 star. That's about 5,200 times the mass of the black hole at the center of our own Milky Way. NGC 4889 is a giant elliptical galaxy, meaning it doesn't have the spiral arms or disc-shaped structure seen in galaxies like the Milky Way. Instead, it appears as a smooth, rounded mass of stars and interstellar material. The presence of this colossal black hole has likely contributed to this shape, as well as to the sparse and relatively uniform distribution of stars throughout the galaxy. Massive black holes, especially those of this size, often play a major role in determining the form of their host galaxies, and NGC 4889's black hole is no exception. At the heart of NGC 4889, the black hole has an enormous gravitational sphere of influence. Stars that pass close to the central region have their orbits altered or even disrupted entirely. For any material that ventures too close, there's a point of no return. Once it crosses the event horizon, it's pulled inward with no chance of escape. As a result, the core of NGC 4889 is a dynamic and intense place where the central black hole exerts constant pressure on its surroundings. Over time, this relentless gravitational force has stripped the central regions of NGC 4889 of much of their star-forming gas. Gas clouds that drift near the black hole can be trapped by its pull, where they become part of an accretion disk. As the gas compresses and heats up, it releases an enormous amount of energy, often in the form of powerful jets that shoot out from the galaxy's center. Normally, a galaxy star formation is fueled by cool gas, which condenses into dense clouds where new stars are born. But in NGC 4889, the central black hole has heated and expelled much of this gas, disrupting the conditions necessary for star formation. The powerful jets and radiation emitted by the black hole's accretion disk have driven gas away from the galaxy's core, creating an environment where new stars struggle to form. The galaxy's current population of stars is likely very old, having formed billions of years ago when conditions were different. Since then, the galaxy has become a place of relative quiet, with little new star formation to replenish its aging stellar population. During an earlier era, likely several billion years ago, this black hole could have been a quasar. Quasars are among the brightest objects in the universe, and if NGC 4889's black hole was once a quasar, it would have emitted such powerful radiation that it would have shaped not only the structure of its own galaxy, but also potentially impacted nearby galaxies in the Coma cluster. Over time, however, the black hole's activity may have slowed as it exhausted the available gas supply, settling into a quieter phase where it no longer shines as brightly. Without enough cool gas to fuel new star formation, NGC 4889 has evolved into a galaxy where old stars dominate, forming a stable but inactive stellar population. In this way, the black hole's hunger for material has shaped the very nature of the galaxy, creating a sort of cosmic desert where new stars rarely emerge. One intriguing question that astronomers are still investigating is whether NGC 4889's black hole is still growing. Although it's no longer as active as it might have been during its quasar phase, there's a possibility that the black hole continues to draw in small amounts of gas and other material. As it does, it may release occasional bursts of energy. These sporadic emissions could reveal clues about the black hole's current state, providing a glimpse into the mechanisms that drive its activity. Black holes, once seen as mysterious cosmic anomalies, are now becoming gateways to deeper insights into the fabric of space-time, quantum mechanics, and even the nature of reality itself. As we push the boundaries of technology and theory, black holes may hold the answers to some of the most profound questions in science. From understanding the origins of the universe to unlocking the potential for interstellar travel, these enigmatic structures are not just the end points of stars, but may also be the starting points of entirely new scientific frontiers. The journey of exploring black holes has only just begun, promising a future rich with discovery and wonder.